Okay, so we know we have a problem in phase 6, but let's look at the other ones first. So there's a good thing to look at this stage is just look at the displacement. So one thing you can plot is that you just plot the total displacement regardless of what direction it is. So that's a kind of useful one to look at to kind of get a general view of what's going on with your problem. So here's our mode. I'd like to turn on the deformed boundary. I like to turn on the cells too because I like to look at the grid. Now this looks like, oh my God, what's going on with my problem here? This looks terrible. But if you look at these displacements, they're all really, really, really teeny, right? So that really doesn't mean anything. And you can make the emphasis of those smaller by hitting Control D. So that's the equilibrium phase. Here's where the facing gets installed, and you say, oh, my facing's installed. I already got a whole bunch of displacements. But again, like these are very, very small displacements. So, and now we're going to do our level 1, where we're going to excavate in level 1. And we're going to have our load installed. And then our strut goes in, our load goes away. Then we excavate to level 2. Our strut goes in, our load goes away. We excavate to level 3. Our load goes in, our strut goes in, our load goes away, and then we excavate to level 4. And it's probably worth at this stage, view, zoom, can I zoom window? Yes, that's what I wanted to do. And now it's really useful to look at several things here. Oh, I didn't want to do that first. Well, that's okay. If you right-click on the strut, you can graph the liner data. And on the liner data, you can graph all kinds of stuff. What we're interested in for the strut is the actual force. And we want to look at it from stage to stage. It doesn't go in until stage 4, so we're going to look at this from stage 4 on. And you can dump these out to an Excel file and plot them yourself. At this stage, it's handy just to look at them here. And so notice what's going on here. At stage 4 is when we install the strut, but there's nothing there, right? Which just dropped in. And then the next stage, which is stage 5, that's when we load it. And notice that it's got a load of it's not quite. We put in 2. It's not quite 2 kips. It's 1.56 kips. Can you see that? That's the load in the strut right now. So when we put the load on there, we dropped the strut and left it off. Some of that load stayed in the soil and it didn't all get loaded to the strut. But we got 1.6 kips in the strut. Y'all see that? I can't highlight it because if I move my cursor, it'll go away. Axial force, 1.6 kips, right? And remember, our load the load we put on the wall was 2. So when I took it off, some of that stayed in the soil. That's okay. And then this stage is a combination. So this is the excavation to the second stage and the placing of the second strut. And notice that when you load the second strut, it doesn't really change the loads in the first strut. And then this is excavation to level 3. and installing the strut at level 3, and installing the strut doesn't change the loads in the top strut, and then this is the final excavation. And we're getting up to about 13, what's the number there actually? 13.4 kips in our strut. And we can do that for each one of the struts. Graph liner data, make sure it's axial force. We want to start this strut. After it's loaded, we'll plot that. So here's the second strut, and this one we put a 2-kip load in the wall, and we got two kips in the strut this time. And then when we excavate down to the next level, that load goes up to 19 kips, and when we excavate down to the third level, that load goes up to 27 kips. And then we're going to plot the third one. Actually, I just need these last 2 levels because those are the only ones that matter. Plot that one. So this one, again, this time when we put two kips in the thing, we got 2 kips in the strut. And when we loaded down the bottom, we ended up with 27, a little over 27.5 kips in the. Okay. So then the other thing you want to look at, there's 2 other things we really want to look at here. One is the liner data, and for the liner data, what's the result that we're really interested in looking at our sheet pile? What are we concerned about our sheet pile? How's it going to fail? Shear? We're going to shear the sheet pile off? Not likely. You guys did a sheet pile wall design. What were you worried about in the sheet pile? Sheet pile going to turn over? How's the sheet pile going to fail? Just bring enough chocolate to share with everybody. Yeah, it's going to yield in flexure, so we want to know the moment in it, right? Man, you guys are either dead or tough or something today. Okay, so we're going to check. We want to check. We don't care about the axial force in the sheet pile. We care about the bending moment. And we want to look at this through all the... we don't care about the equilibrium phase. We don't really care when it's installed, but we look at all the other ones. So here's the moments in the sheet pile through all those phases. And the maximum moment is 4.7 kip feet. Is that okay? How would we know? Divide by section modulus and see if it, see if it exceeds our yield stress, right? So somebody jot that down, because I haven't checked this yet. 4.7 kip feet. Because I told the program not to let the sheet pile yield. So we're going to have to check this one by hand. Okay. What's the other thing we should be concerned about? There's one other thing that we should be really concerned about. Well, maybe 2 things. What's our other big concern with excavation support? What, displacement of the sheet pile and displacements? Where? At the surface, right? So we're concerned about displacements at the surface and displacements at the sheet pile. So we can check the sheet pile. We're not actually that concerned about displacements. We're not as concerned about displacements in the sheet pile as we are about moment. We'll check that, but we can graph displacement of the sheet pile. That's easy. That's just displacement of the sheet pile. And let's just check it for the last one because I'm feeling lazy. So there's the total displacements. How much displacement are we getting in the sheet pile? Well, the highest displacement we're getting in the sheet pile is 0.21 feet. So about 3 inches. Is that okay? I don't know. What does it matter? 3 inches might be okay. The more important one we'll worry about is displacements where? What's the other displacement we're really worried about? Well, we can check the base displacement. We're generally more concerned about this. Ooh, I've got a bad boundary. I got some bad boundary conditions in here. I didn't see those. How did I get these fixed boundaries in these ones? We'll have to go back and fix that. We're concerned about the displacement at the ground surface. So we're going to put a material query across the ground surface. And we just picked two vertices, so I'm going to tell it to plot at 30 locations along. And when you do this, it's just plotting whatever quantity you're looking at here. So if we looked at the strain, it'll plot the strain. And we were looking before at total displacement. And we don't really care about the total displacement of the ground surface. We really care about the vertical displacement. So we need to come in and change this to vertical displacement. And now this across the top is showing our vertical displacement. So we can graph those data. I'm just going to plot the excavation ones because that'll be enough. So here's our settlement curve outside of outside of the excavation, and there's some model things that are going on here that are a function of some problems with our model. But so at the very beginning, when we unload, the soil at the surface actually gets relieved and it moves up. And then there's something funky going on with the node at the pile, and it's getting dragged up during the pile as the pile is moving up somehow, and the node there is getting dragged up. So there's something that's not right about that, and I haven't figured out exactly what's wrong with that. But the one we're more interested in is this displacement outside here. So we're getting a peak displacement here that's about 6/100ths of a foot. So it's about a 1/4 of an inch, right? If we believe that. So that looks like it might be okay. But this is the only way. The only way that you can get displacements outside the excavation is by doing this kind of analysis. If you're not going to do a finite element analysis, then you're stuck with using those charts from is it Duncan? I think that's right. The empirical fits for the historical data. That's the only way you can do it is with this. But this is really, really sensitive to how you set up your problem. I want to show you that in a second. And then I'll turn you guys loose to do some other stuff. Okay, so let's go back here to our problem. I'll save this on a file, save as. I'm going to do two changes to this. I don't know, I didn't notice this before, and I don't know how. I don't understand how we got some fixed boundaries in here. Oops, that's not what I want to do. These got pinned, and they shouldn't be pinned. Oh, I know I got to do this. I forgot to do this. If you just want to change a single node, you right-click on the node. All right, I'm going to change. I put two different. If you go to properties, I want to talk about two different property issues here. One is on materials. So I took some data from the literature for this Karlsruhe sand, which is a loose sand in Karlsruhe, Germany, if you've ever been there. If you haven't, it's still a loose sand from Karlsruhe, Germany. And I put two models in here. One's just a simple Mohr-Coulomb model. So we have a very simple Mohr-Coulomb model. It's got a peak friction angle of 33 degrees. I put in a very small cohesion that just kind of helps make the problem stable. And then we made it a plastic material. Says it's got a residual friction angle of 30 degrees, same cohesion, and then a dilation angle of, have you guys in 532 started talking about dilation angles yet? In sands? No? Well, don't worry about it. I put, it's got a dilation angle 30. The dilation angle is generally, can be estimated as 30 degrees, the friction angle minus 30 degrees, so it's got a small dilation angle. But it's just a Mohr-Coulomb envelope. And then the second one I put in was a hardening model that had a hardening model with a cap model in it. And I gave you a paper to read about that. And so what this does is it allows yielding it allows the soil to yield at low stresses before it actually hits the Mohr-Coulomb envelope. What it really does is it allows the Mohr-Coulomb envelope to grow and harden as it. So this is a very important parameter this is a very important model behavior to capture if you want to really get displacements correct in soils. So I'm not going to explain that, but I gave you a paper to read about it so that you'd understand why it was important. So that's the model I was using for this one. I'm going to go back and change to the really simple Mohr-Coulomb model here. So we're just going to change to this all to the Mohr-Coulomb model. And we're going to rerun the, whoops. And we're going to rerun the calculation. So these are the it's the same material, except in one case I'm capturing some of the nonlinear behavior of the material, and the other one I'm not. All right. And now we're going to rerun the problem. I say there's something else. Okay, what's one thing you notice immediately about the difference between the simple soil model and the more complicated one? How long did it take to do the computation last time? A lot longer. Right, okay. Whew, I thought maybe you were all dead. Oops, it didn't converge one place. Where didn't it converge? What does that mean? I have no idea what that means. So I want to look at vertical displacement. Oops, I forgot to tell it to excavate. Let's go back and do that. Maybe that's why it was converging fast. Forgot to tell it to excavate. Level 1, excavate. Level 2, excavate. Level 3, excavate. Level 4, excavate. All right, let's try again. All right, now I want to look at the vertical displacement. Now you're going to see something really interesting, I think. Okay, so now I'm going to do a query, a material query from here to here. We're going to look at this at 30 points, and we're looking at the vertical displacement now. Now we're going to plot the vertical displacement. And now, what's the vertical displacement look like now? Remember what it was on the last one? Yeah, it was quite a bit. It was quite a bit more here. So the calculating here, the lesson I want you to get out of this is calculating the vertical displacements outside of the excavation is really highly depending on having the right soil model in there. Because this is the same model. One's just a simple Moore Coulomb model, and one's a strain hardening model, and you get very different displacements. So it's really important when you're doing this that you get a good soil model. All right, so what I would like to do now is take a break. And then I think what I was going to do is let you guys take this model and I still got one thing I messed up down here. And I thought I'd give everybody a little thing to do with the model. So let's take 5 minutes, and then when we get back to that, I'll give you each. I'll get you guys into groups, and you can do some look at some different stuff with the model. Okay. So we're going to take a break.